Hi guys, this is the first multiple choice packet. These packets serve several purposes. They will be sort of like notes. There will be notes in them to review old topics and to remind ourselves how to do them and then practice. And we will probably end up doing like half the assignments together. If you just follow this video and do the notes and do the problems, I'll give you chances to try them on your own and then we'll do them together. And then you'll finish the other problems that we didn't do on your own, and then you can check your answers and work online. So these are just good review, just good review assignments. You're going to be doing about one assignment a day, not necessarily multiple choice one every day. But so AB number one, the derivative. This is sort of like the beginning of it all. We did derivatives last semester. So what do we need derivatives for? They monitor change. They measure change, maybe over time, on some applications. But essentially, derivatives they're change in something versus change in something else. So they're rates. They are related, so we might have a function f of x. And so the derivative is going to measure the change of y versus x, and that would be the slope of a tangent line. So that's how tangent lines are related to them. So derivative isn't the tangent line, but it's the slope of the tangent line. They both, the change in the tangent line matches the change in the function at that point. And the interesting thing is if we zoom in close enough on a curve, it'll actually start to look like a straight line. And that idea is called local linearization. And it kind of helps us in some of the different foundations of these different ideas. The definition of the derivative, the slope, which equals the derivative, is we take a point near this point, and I think I'm going to show that over here. Actually, I'm going to go over here first. So tangent estimates slope and the y value of the function near the point. So I'm going to draw this picture again. We have some kind of curve, f of x, x, y, and we want to know the slope at some point x. Okay, now we know that the tangent line gives us, the slope of the tangent line gives us the exact answer. But to find the slope of a line, we need 2 points, and we only have 1 point. So what we're going to do is we're going to find another point further nearby, connect them. That's called a secant line. And that line is an estimate for our actual answer. And the closer we move this, the better that secant line gets, and the closer it gets to the real answer, until if we can move it as close as possible, then we're going to get the exact answer. Now, I'm going to represent the distance of this other point away from the x as h. So the coordinates of this point are x plus h. The coordinates of this point right here are x, f of x. And this one's going to be x plus h, f of x plus h. And so then if we wanted to find the slope of one of those secant lines, whatever they are, I'm going to go over here and we're going to say, okay, we're going to leave some space here, by the way. We're going to leave some space, f of x plus h minus f of x, rise over run, over, I'm going to just write here, x plus h minus x is going to leave you with h. Now, this is an estimate, but if we move this second point, x plus h, infinitely close to the first one, then it approaches the exact answer. So that's where the idea of a limit comes in. The limit as h goes to 0. And this is the definition of the derivative. Now, there's a few other versions of it. That's a right-sided definition. You could use a point to the left instead, and that one would be the limit as h goes to 0 of f of x minus h over h. That would work. Or you could use a symmetric one where you use a point to the right and a point to the left. So that'd be the limit as h goes to 0 of f of x plus h minus f of x minus h, but the run is now 2 h's because that's the distance between them. So that's a symmetric definition. These are called difference quotients, by the way, which is just a fancy word for a fraction with subtraction in it, difference quotient. Now, the other thing that we can do, and we haven't used this a lot yet, is that we could use this tangent line. See this original tangent line. I'll try and darken that in. This original tangent line. What we could do is we could use a tangent line to approximate the value of the actual function. So this is the actual value of the function at some later point. But we could use the point on the tangent line as an approximation for this, or an estimate for it. There's an error, of course. It's not going to be perfect. This is an overestimate because it's bigger than the actual value. And if our tangent line was below the curve, then it would be an underestimate. So how do we know if it's an over and underestimate without having to have a picture? So I'm going to just draw just a generic curve right here, and we could start to see what's happening. So if we do a tangent line here, that's an overestimate, right? Any point on here is going to be above the actual curve. If you do a tangent line here, it's going to be an overestimate. If you do a tangent line here, it actually ends up underneath, and that's an underestimate. And if we do a tangent line here, that's an underestimate. Any point on there will be below the actual curve. And if we do in here, that's an overestimate. What's the thing that is influence whether the tangent line is above or below the curve? It's just concavity, right? So it's purely concavity that if we know, we got to know that the concavity is down for that whole chunk, not just where the tangent line is, but also all the way until the point we're trying to use it to estimate. So if it's concave down, you're going to get an overestimate every time. And if it's concave up, you're going to get an underestimate. Now, I wouldn't memorize this because you could just draw a simple picture of a concave up or down curve with a tangent line to it and decide if it's above or below it. Okay? This is not a formula to memorize. It's more of an idea that you understand that the tangent line has y values that are above the curve. So now we're going to do problem one together. And so this is a limit, and you might think, oh, okay, let's just plug h equals 0 in because that's usually kind of the first thing we do. Just evaluate by substitution, and you get sine of pi over 3 minus sine of pi over 3 over 0 equals 0 over 0, which is indeterminate. Now we could use L'Hopital's rule to find it, but what would be better is that we realize that this wasn't just any old limit, but that limit looks really kind of specific. And that looks like a derivative, right? Do you see the same function with something plus h minus the same function over h is going to 0? That's the definition of derivative. So if we can recognize that, we could do this problem a lot quicker, probably more correct, and say, okay, well, what's the function that we're trying to take the derivative of? And you see it there twice on the top. Now, there might be x's, x plus h and x, or there might be values where the x's go. Now, if there's values where the x's go, that just means one more step to do later. But imagine that there's x's there first. And the function is sine x, because here it is with x plus h, here it is with x. And you're like, well, I know the derivative of sine. That's easy. That's just cosine. And then if it had x's in it, then that would be your answer. But since there's values where the x's are, that's something we're now going to do after this. We're going to evaluate the derivative at pi over 3. Now, hopefully you guys, I don't know if you're rusty in your trig. This is a cosine curve. 1, root 3 over 2, root 2 over 2, 1/2, 0, pi over 6, pi over 4, pi over 3. So this is the one we want. That's 1/2. You got to know basic trig for the AP test. Okay, now what I want you guys to do is I want you to try the next problem Okay, and I want you to go ahead and pause the video right now to give yourself a minute to try it, and then unpause it, and I'm going to go ahead and do it. So go ahead and pause it. All right, so I'm going to do it. Let's see, that's a derivative. Not that you have to write this, but it's derivative. What's the function? The function is x cubed. What's the derivative of x cubed? 3x squared. And then they tell you separately to evaluate it at 2. So then we're going to plug 2 in after we've taken the derivative. And we get 12. So, all right. Let's do a little more, another chunk of notes in the middle of this assignment. Variations of forms of lines. Now, we have to deal with a lot of lines, especially tangent lines. And of course, we can write lines in slope-intercept form, which sometimes we do because it's convenient for graphing or evaluating values. But usually, we're going to do point-slope form first, and a lot of times just leave our answer like that. So, I mean, this is our favorite point-slope form. Slope-intercept sometimes, but it's easier to get point-slope from a point and a slope. Unless it's the rare occasion where you have the slope and the y-intercept, you know it straight out. Okay. Now we deal with tangent lines are parallel to the curve, right? They're parallel, they have the same slope. Normal lines are perpendicular to the tangent line. So if you have a curve, this is the tangent line at that point. And then this is the normal line to that point, and it makes a right angle. Anyways, okay. Now, I think we're going to... I want you to... let's see. I want you guys to go ahead and try number 4 and 7 right now. So pause the video and try 4 and 7. And after you've tried 4 and 7, unpause the video and I will do them. And you can figure out if you got them wrong or right and fix them. Or if you got stuck, you'll figure out how to do them. All right. So go ahead and pause it. All right. Now you've tried it. So let's see. We have a point, right? That's an XY pair. We have a derivative, which is the slope. Find the equation of the tangent line of f of x at x equals 5. So you got to realize, sometimes they just straight out give you the y value. So this is going to be y minus 7 equals 2 times x minus 5. And that's good enough. Like on AP test, for response, leave it. Now, if it's multiple choice, then you might have to write it in some other form, which might be slope-intercept. But it might be like standard form or some other weird form that doesn't even have a name. So you're gonna be at the mercy of the way they answer it. But there you go. So you guys should have tried number 7 already. So we'll do number 7. Number 7. What is the 50th derivative of cosine x? It sounds like. Now, hopefully you guys remember these. Like the intention isn't for you to do 50 derivatives, but that must mean there's some kind of pattern so that we could kind of predict what it's going to be. And what you might do is start taking some of the first derivatives to figure out what the pattern is, or even verify that it is what you think it is. So cosine is sine. Now, this is like the 0th derivative, by the way. Negative cosine x. Third derivative is positive sine x. Fourth derivative is cosine x. And what you should notice is that we're now back to the top of the list. So we have this repeating pattern that happens. There's 4 different outcomes and then it repeats itself. So what we want to do is say, okay, well, every 4th derivative, we're back to where we started. So let's figure out at the very end how far we're into that last chunk of 4. So we take 50 and we divide it by 4 and it goes in 12 times, and it's 48, and the remainder is 2, and the remainder tells you what derivative. That means that the 50th derivative, which we'll often put in as a superscript in parentheses, because we don't want to put 50, prime marks, that this equals the same as the second derivative of x, which we have up here is negative cosine x. So, okay, let's look at number 6 together. The local linear approximation. That's another word for tangent line approximation or estimation, or use the tangent line to estimate the function. Essentially, it means just we're using a line, linear. Local means nearby. Tangent line to approximate a curve. And so that's that idea that if you have a curve, you have a tangent line, right? And then you want to estimate this value with that value right there. And then there's an error involved that makes it over or under the actual value. Now, it depends if it's concave up, concave down. This says f will always be greater than or equal to the function's value if for all x in the interval containing the point of tangency, which thing is true. So we were talking about that it has to do with concavity. So it's definitely, I think, these two. It's not if it's increasing or decreasing. It's not if it's a critical point. It says that f will always be greater than the actual value. And so we actually just drew an example here where all the things are greater than. It's when it's concave down. Okay. Number 8. Let's see. I want you guys to try number 8, 12, and 13. So I want you to try number 8, 12, and 13. So pause the video, try those. There's some derivative examples, but they're also multiple choice, so you're kind of at the mercy of the answers. So pause the video, try 8, 12, and 13. And after you've tried 8, 12, and 13, unpause the video. If you don't pause your video and you just copy what I'm copying, well, great, but I'm not going to be there when you take your test to just so you can copy down my work. So you need to try them yourself. All right, go for it. Okay, so you've tried 8, 12, and 13. And so I'm going to try them. So we're looking for the derivative here. And there's a function inside of another function. So we got to do chain rule. So we do the derivative of the outer function first, right? So function within function, you got to do the chain rule, right? You got to do the chain rule. So that means you do the derivative of the outside first, leave the inside the same, then you got to multiply by the derivative of what's inside. Now, I got to be careful. You might put parentheses. This is going to be 4x to the first, derivative plus 1 is 0. If there's multiple terms, then they have to all get distributed. And that was just a super common mistake back first semester when you guys were trying to learn how to get good at this. Now, before we try and cube this, look at all the answers. A lot of times you want to look at the answers maybe even before you start it or early on to say, okay, this is what I'm trying to get my answer to look like. Not the way I might think I would usually write the answer. So this is 16x, 2x squared plus 1 cubed. And that one is on there. Okay, so there we are. And then you guys tried 12 and 13. So 12, we got another derivative. We're looking for the nth derivative. So this is kind of like that 50th derivative cosine idea that there must be some pattern. So this time we're actually looking to write a formula for any derivative. So I would say the best plan of attack is to start writing the derivatives out to see if you can establish a pattern. So the first derivative is going to be x times, now this is a product rule, x times derivative of e to the x is e to the x plus e to the x times derivative of x is 1. And then the second derivative is you got to do that product rule. X times derivative of e to the x is e to the x plus e to the x times derivative of x is 1 plus the derivative of e to the x is e to the x. Now what you might do is rewrite this more simplified. So we got this, we got this, we got this. Third derivative, if you want, maybe you're starting to see the pattern. Derivative of this is going to be x times e to the x. Derivative of e to the x is e to the x plus e to the x times derivative of x is 1 plus derivative of 2e to the x is 2e to the x. If we simplify it, we get x e to the x plus 3e to the x. You guys see the pattern here? I think this is like 0 times e to the x, 1 times e to the x, 2 times, 3 times, and they all have an x e to the x. So I think the nth derivative is going to be x e to the x plus n times e to the x. That's my answer. Now I look at the multiple choice and I don't see it. So then I think, well, maybe it's there. I just need to manipulate this to make it look like one of those. A couple of these have parentheses. So maybe there's some factoring. Like, oh, I could factor an e to the x out. Right? So there you go. Answer C. Okay. I want you guys to also try... let's see. Did you guys try 13 already? So you should try 13. Let's do 13. Let f and g be differentiable functions. That means the derivatives exist everywhere, which means they're also continuous. They give you some values. F of 1 is 4, g of 1 is 3, f prime of 3 is negative 5, f prime of 4 is negative 4, g prime of 1 is negative 3, g prime of 3 is 2. And then they give you this new function, h. H equals f with g inside of it. And they want you to find h1. Well, the first thing I would do is I'd write an expression for h prime of x. And this is a chain rule problem. This is the derivative of the outer function first, leave the inside the same, times the derivative of what's inside. This is a way for them to test you about the chain rule without having to mix other rules in at the same time. So then h of 1 equals, and I'm going to substitute 1 in for all the x's. And then we have to evaluate what's inside first. So g of 1, it was 3. And then f prime of 3 is negative 5. And g prime of 1 was negative 3, which gives you 15. All right. Okay. I want you guys to try 14 now. Maybe 14 part A. Do 14 part A. This is called a function table, and these are pretty popular on the AP test. This is a way of pretty much kind of doing what we just did on the last problem, 13, but giving you all the values in the table. So this is just a way to organize all the values, but you're working with, you got to find, so try 14A right now. So the first thing I would do is I would just take the derivative in general, and it's a quotient rule, low d high minus high d low all over low squared, which people love to forget. They just forget it. And it's always subtraction. People put addition. Now, if we want k prime of 3, well, we could just write this f of 3 times g prime of 3 minus g of 3 f prime of 3 over f of 3 squared. We're going to look these values up in the table. So f of 3 is 1, right? G prime of 3 is 2. G of 3 is 3. F prime of 3 is 0. And f of 3 is 1 squared. So the answer is 2. So We did a bunch of these, but it's been a while. But they come up on the AP test, so I just want to make sure you guys remember how to do those. So I'm going to let you guys try the rest later. Let's go to the last page and talk about the difference between explicit differentiation and implicit differentiation. So we're going to go ahead and start with problem 15. And we're going to say, all right, x plus y equals xy. And we're going to try and find the derivative. Now, I'm going to ignore the answers right now. If we want to do it explicitly, that means we need to get y equals, as a function of x alone. We need to isolate y to do it explicitly, which is the way we usually do it. So you'd want to, okay, well, how are we going to get y by itself? Well, you probably want to group the y's together on the same side. We can't combine their terms because their coefficients aren't like each other, but we can combine them by factoring the y out. And then y equals x over x minus 1. And then we could take the derivative, dy dx. I'm going to do quotient low, d high, minus high, d low, all over low squared. I'm really generous with parentheses on quotient just because there's usually a lot of terms that need to be distributed and things like that. So this is going to be 1x minus 1x is 0. So it's going to be negative 1 left over, and x minus 1 squared is our answer. Now, if we look down here at these answers, that one's close, but it's not on there. And I don't think there's any way to really change this to look like any of those. Generally, if you're given an equation like this, it probably means you're going to do implicit, which we're going to talk about right now, which probably means the answers are going to have x's and y's in them. If you look at the answers and they have x's and y's in them, you're not going to get that kind of answer from explicit. Explicits will only have purely x's. So let's remind ourselves how to do explicit differentiation. So implicit. So implicit is like we're just going to start taking derivative with the y's in the middle of it. Now we're taking the derivative with respect to x. So the derivative of x with respect to x is 1. The derivative of y with respect to x is the derivative of y. We're going to usually write it as dy dx. Okay. You don't want to put y prime because that looked like a y to the first power, and we are going to have y to the first powers in our work. So that can be really potentially confusing. Over here, we got to do product rule, right? And we're going to do x times derivative of y is dy dx. Plus y times derivative of x is 1. So anytime you encounter a y when you're taking the derivative, you're going to get a dy dx. This is what we want. So now we got to get those together and get all the other stuff on the other side. So we could say, let's subtract y over here. Let's subtract this dy dx over here. They don't cancel each other out. We're trying to combine them together. That's what we're trying to find. So we're going to factor out the dy dx. Similar to the strategy we used over here to get the y by itself. And then we're going to divide both sides by x minus 1. Now, let's look over here. That's answer C, right? Now, if we had moved things to the other side, just real quick, if we had done dy dx minus x dy dx equals y minus 1, just to show you potential confusing thing at the end, because this is totally correct too. You could do this. This is totally correct. But if you look at the answer list, y minus 1 over 1 minus x isn't there. So what you need to realize is like, oh, well, maybe if I multiply or divide the top and bottom by -1, which just changes the signs of everything, I'll find my answer. So just watch out for that. Okay, I want you guys to try number 16 right now. Okay, just try it on your own. Pause the video, try it. Okay, assuming you've tried it now. So we're going to do implicit. I think that's just our best bet because I don't think we're going to get y by itself very easily. It's not going to happen. So the other reason is you're not going to do explicit because it's just too difficult or impossible. So we're going to take the derivative. The derivative of y squared is 2y to the first. Now that's an outer derivative. This is like chain rule, and then you got to follow it by the derivative of what's inside, 2y dy dx. You don't want to get 2 dy dx. You got to do the outer derivative first, 2y to the first power. The inside stays the same. The inside is the y. Now the y is some function of x, right? It's kind of like we're doing that, right? And we know that we could write it with x's potentially. And that's what this represents afterwards. It's chain rule, okay? Minus, now be careful here. This is going to be a product rule, and you got to subtract it all. So you might want to put parentheses. So ignore put the minus here, ignore it. 2x times derivative of y is dy dx plus y times derivative of 2x is 2. You could apply the 2 to either part. Equals derivative 21 is 0. Don't put 21. Now we're trying to find dy dx. We need to distribute the multiplication or the negative subtraction. We can get the dy dx's together. Now that's a y to the first power. That's why I'm not using primes here. 2y minus 2x equals, this is a minus 2y that we're going to add to the other side, positive 2y. So dy dx equals 2y over 2y minus 2x. Then we want to evaluate at xy, and they gave us an x and a y value, which works nicely because we need the y as -3 and the x is 2. So we get -6 over -6 minus 4 equals -6 over -10 equals positive 3/5. Positive 3/5. The other possibility is that instead of doing all of this, as soon as now, if we had to find dy dx just as an expression, then we'd have to do all this. We would stop right there. But instead, we could just, after we've done the derivative, we could just start plugging in the x and y values right now before we try and solve it. And it'll give us lots of numbers, which will be easier to finish. So we plug -3 in for the y, and then you still have a dy dx minus 2 times x is 2 dy dx minus y is -3 times 2 equals 0. And so then we have -6 dy dx minus 4 dy dx plus 6 equals 0. So then we're going to get -10 dy dx equals -6. And we divide both sides by -10 and get our answer. I just find that to be a lot less complicated than trying to solve with all these different variables involved. If it's just numbers, that works a little easier. That's it for this. These office hours for this, teaching you. We did some notes. We did some problems together. I'm going to have you guys try all the rest of the problems on your own. I think you have a lot of good review now to help you do those. I'll post the answers and work later so you can check them. The answers should already be up. Okay.